So we keep it quite informal. So can we interrupt you at any
You can
time,
interrupt me, and you can tell me when I've been talking for too long and we need to move on.
Okay.
Because it may be a little bit on the long side, because it was a longer talk before. So we'll see. We'll see how we get on.
Yeah, it's fine. Okay, thanks.
Okay, so yeah, I'm going to be talking a little bit about the work that Tita and I have recently put out with his student Antoine. And this is all about perturbation theory in the complex plane, and how we can use that structure in the complex plane to improve our estimates of our perturbation energy. So we're going to be using, come on, there we go. We're going to be using a very simple model to understand this perturbation theory, and this should be hopefully familiar to most of you. This is the Hubbard dimer, and it's a very simple model for our H2 molecule, and it's only got two parameters here. And this is the on-site electron repulsion, which basically gives you a penalty for having both electrons on either the left or the right, and a kinetic energy hopping term, which gives us kind of the delocalization energy of our model. So the on-site repulsion is a two electron interaction, and the kinetic energy is really a one electron interaction. And the ratio, the ratio of these two parameters is our correlation strength, U over T. So if we take a particular example, U over T is 4.5, we get an exact energy of minus 7.60. But if you take the Monoplastic series using the restricted Hartree-Fock reference, you'll find that these energies at each order don't really get anywhere near to our exact energy. And in fact, they're eventually going to diverge. But I'm going to show you...
Already interruption. But the exact energy is for T is 1, I guess, or?
Yes, so these are all in units of T.
Okay.
So our final best estimate, so I'm going to show you how by the end of the talk, we can get a final best estimate of minus 0.76042, which as you can see is pretty close to the exact value. So just to get our notation all in the right place and make sure we're all, well, I'm sure we all know about monoplastic theory, but we essentially are looking at solving the Schrödinger equation using a perturbation Hamiltonian, which we've decomposed into a sum of a reference and a interaction term here. So the strength of our perturbation is controlled by lambda, and we're essentially going to expand our exact wave function and our exact energy in terms of power series of these lambda terms. And we can see that here where we introduce the different orders K. So monoplastic theory is simply a particular partitioning of this Hamiltonian, where we use the Fock operator as our reference Hamiltonian, and we use usually the Hartree-Fock determinant as our reference wave function. And we have our first order energies, which are equivalent to the original Hartree-Fock energy, and of course the second order correction that hopefully we're all very familiar with. So to get an idea of these reference states, there are kind of two main reference states we might consider today. And these are the restricted Hartree-Fock solution, where we have symmetry pure and closed shell orbitals. So these would just be kind of a sigma g squared state. And we also have this unrestricted Hartree-Fock solution where we allow the electrons to occupy different orbitals for different spins. So what you can see is that the restricted Hartree-Fock solution is the Hartree-Fock ground state when you get to small correlation values. And this is exactly where we know that Hartree-Fock performs well. But as we go towards the kind of larger correlation, we see that the unrestricted solution becomes the lowest energy. And this unrestricted solution doesn't even exist below U over T is less than 2. And this is what we call our Coulson-Fisher point in the H2 molecule. It's worth remembering that the UHF wave function is actually doubly degenerate. So we have one with the alpha electron on the left and the beta electron on the right, and then we flip the spins of those two states. And because we have the different orbitals, we have spin contamination in our wave function. So S squared is about 1 in the U over T infinity limit. So if we take the restricted Hartree-Fock solution and we use it as our basis for our, or as our reference for our monoplastic theory, we can see that actually at u equals 3/3.5t, we get a very quick convergence towards the exact energy. And here we've got the different contributions coming at each order of perturbation. But if we go to 4.5t, which was our original example, you can see that they start to converge relatively okay, but as we go to large orders of perturbation, they really diverge quite catastrophically. So something strange is happening between 3.5 and 4.5. And we might think that our unrestricted reference will be better because we've got a better reference energy. But if we take our unrestricted reference, we see that, well, we get a very slow convergence towards an exact number. And this, in fact, is just oscillating over a massively long range of perturbation orders. So this is up to 200 orders, and you're still seeing corrections coming in. So in fact, this slow convergence of unrestricted monoplastic theory has been known since early works in the 1980s and has long been thought to be kind of caused by the spin contamination in the wave function. But to understand these theories, we're going to take a look at what happens in the complex plane. So when we extend our models to the complex plane, we're going to be looking at what would be a non-Hermitian electronic structure theory. And just to give us a bit of a kind of feeling of what change this makes to electronic structure, we can look at the Hilbert space for our Hubbard dimer, and we can look at the exact Hamiltonian in this Hilbert space. So just to get us all in the right basis, our Hilbert space here has 4 configurations. So we have both electrons on the left, one on the right, and both electrons on the right. And we can build the exact Hamiltonian, and it's quite a simple Hamiltonian here. And we've introduced a coupling term lambda, which is introducing the off-diagonal terms to our expression. So when lambda equals 0, this is a diagonal matrix, and the FCI energy is going to arise when lambda equals 1. And we can derive from this Hamiltonian the exact expressions for these energies. And you can see there's this pair of energies which have a square root term here in terms of the t squared and u squared parameters. And these are our singlet ground state and highest excited states. And then we have this triplet energy, which is independent of lambda, and another higher energy singlet, which is independent of lambda. But this square root term is going to be really important, and it's going to turn up a lot throughout many different examples later in the work. So what do these energies look like as a function of lambda? Well, if we look on the real axis, we see this kind of classic avoided crossing shape. And the avoided crossing happens at lambda equals 0, which is where we have no interaction between our states. But if we extend lambda into the complex plane, and when we do that, we turn our Hamiltonian into a non-Hermitian Hamiltonian, we find actually this remarkably bizarre looking structure with a degeneracy in the complex plane. So this degeneracy occurs at u equals 2t or 2ti. No, that's sorry, 4ti. And it's indicated by this black dot. And it is an exact degeneracy, which means that the two states are, well, exactly degenerate. And in fact, the wave functions are also equivalent and exactly the same at that point. So the reason you get this degeneracy, hopefully you can see, is because the square root term goes to 0. So if we're considering this exact energy as a complex energy function, we would call this a square root branch point in the complex plane. And indeed, the correct way to be viewing our many to one or one to many FCI energy surface is as one of these complex functions, where we see that the discrete states on the real axis are unified in the complex plane as this so-called Riemann surface. So these non-Hermitian degeneracies are known as exceptional points. And the really incredible thing about them is that if you follow a pathway around an exceptional point, we'll move from our ground state energy surface to our excited state surface. So we can swap.
I have a question. So in this figure on the right, you say the degeneracy is at the black spot, but then I see there are more than one values for which they are the same excited and ground state. I mean, how do you?
So this is quite an important point and is not clear from this particular figure. These are complex energies, and this is the real energy that is being shown to you. So there's an imaginary component to your energy, and you have a real degeneracy along that line, but the imaginary component becomes different.
Okay. Yeah.
So that's exactly why. And indeed, if you looked at the imaginary component, that would become degenerate in the opposite direction. Okay, so we can look at these degeneracies in Hartree-Fock theory itself. So it's not only an exact theory where we can see these things. So if we were to look at the UHF approximation, we're building our Hartree-Fock orbitals as self-consistent eigenfunctions of our Fock operator. So here we have the core Hamiltonian, and then we have the kind of 2-electron interaction term, which is our Hartree-Fock potential, and we have orbitals which are then self-consistent eigenvectors of that Fock Hamiltonian. So if we look at our UHF symmetry breaking point, we can parameterize the orbitals using these rotation angles, which mix in the left side and the right side into our Hartree-Fock orbitals. And these rotation angles are a function of, there's one for the alpha orbital and one for the beta orbital. So when we're looking at our weak correlation regime, where our restricted reference is our ground state, we see that both of these angles is just pi/2. And our energy is this linear term in terms of U and T. But if we go to our strong correlation regime, we find these two lower energy UHF solutions, and the rotation angles have this complicated arctangent form, where again you see the square root term arising on the denominator. So if we extend, or if we introduce the coupling term again with our lambda value, and we couple the Fock parameters, the kind of self-consistent term using a complex lambda value, we see exactly the same structure in the complex plane. So when lambda is equal to 1, and this symmetry breaking event occurs, we see that an exceptional point appears in the complex theta plane.
Sorry, can I interrupt you 1 second?
Mm-hmm.
No, okay, so you are solving now this Hamiltonian. Okay, you are really looking now for the, let's say, psi lambda, the ground state.
Yeah.
Yeah, no,
So,
yes, it's not, okay.
So this is your optimal UHF rotation angle.
No, because in some of your previous work, you had done something different.
Yes, you could.
Yes,
do all of this.
You were solving the Hamiltonian with a given lambda for the interaction with Hartree-Fock at that interaction. But here you are really doing the Müller-Plessis wave function.
So in this case, this is still Hartree-Fock.
Yes,
I just want to show that these multiple solutions also exist in our Hartree-Fock world, and you get the same sort of exceptional points even in a Hartree-Fock approximation. So this is
okay. No, then it's not fully clear to me. 1 second.
So I think, Paola, you're right, actually. So we solved the Schrödinger equation for the Hartree-Fock equation for each lambda value.
Yeah.
Okay. Yes. So as if the physical system had lambda in the electron-electron interaction. Okay. Yes.
So yeah, we see exactly the same behavior in our multiple Hartree-Fock solutions, with exceptional points occurring on the real axis. But yeah, it's probably wise to get back to monoplastic theory at this point. So how does this really relate to our monoplastic expansion? Well, we need to view our monoplastic energy as a function of this complex lambda value. And again, we have the exact energies at lambda equals 1. And at this point, our monoplastic energy is multi-valued, and each of the different solutions are our ground and excited states. So when we take a monoplastic series, all we're doing is a Taylor series expansion of this energy function. And of course, our Taylor series expansion is only going to converge if lambda equals 1 is inside our radius of convergence. And we know that the radius of convergence is controlled by the closest non-analytic point in the complex lambda plane. And this is usually the magnitude of the closest singularity, pole, or essential singularity or branch point in the complex lambda plane. So as a simple example, we can look at the simple function 1 over 1 plus x to the 4, which you can see is smooth and real on the real axis. But if we take our Taylor series approximations of increasing order, we see a catastrophic divergence at x equals 1. And this is exactly due to the existence of these complex poles when the denominator goes to 0. So what does this look like in our restricted monoplastic series? Well, here we can derive the exact expression of our RMP energy with this complex lambda parameter. And again, you see this square root term appearing in the energy. And if you take lambda equals 1, this will recover your exact FCI energy. So you'll notice that this square root term goes to 0 at these exceptional points. And these exceptional points are in the complex plane at 40 over u. And you can see this here. Again, there's a black dot. So we have the two singlet state energies interacting with an exceptional point in the complex plane. So what we see immediately is that lambda is going to create a radius of convergence, which is exactly controlled by the strength of our correlation. And we can see that when we are diverging for u over t greater than 4, we see the exceptional point just comes inside our kind of radius of convergence, which is this cylinder. And on the other hand, if we're inside, so u over t is 3.5, we get a convergent series. And this exactly explains what we saw in these original perturbation expansions. So the radius of convergence is controlled in this case by an exceptional point between the ground and the double excitation. And we can think of this as the avoided crossing on the real u over t axis. So what about if we look at our unrestricted monoplastic expansion? Well, now, because we've broken the spin of our orbitals, we get many more interactions between different states in the complex plane, because we don't have symmetry restrictions making those interactions 0. So here we see now that there's an additional exceptional point which appears between the excited state and the first excited and the doubly excited states. And at the same time, we see that the interaction between the two lowest energy states shifts outside the radius of convergence. And in fact, for everything you look at, for all different u over t values, you'll find this exceptional point appears outside that radius of convergence. So the UMP expansion will always converge, but it will converge increasingly slowly as it converges, as this point moves closer to the radius of convergence. So on the other hand, if we were to look at our excited state convergence, so take this as our reference point and on the blue surface, we would find that it always diverged, because that second exceptional point is always within the radius of convergence. And indeed, we can look at the radius of convergence for each of the different states simply as a function of u over t, and we see exactly what I've just described, where the ground state is always convergent, and in certain cases, the excited state is usually divergent. And what we can think of is having said that by breaking the symmetry, we sacrifice excited state convergence to improve ground state convergence. So we've seen that there are two kind of different types of convergence that appear in our monoplastic series. There's this UHF version, which is very slowly convergent, and then there's the RHF, which was quite oscillatory and, on the other hand, relatively rapid. Now, the first really kind of systematic way to classify Monoplastic theories was done in about 1996 by these guys, Kramer and Hay. And they found two main classifications of monoplastic theory. And the first is what they called this class A type of system. And in here you find this monotonic convergence, and this is on the left. And what they argued is that this monotonic convergence in a class A system is driven by pair correlation with low contributions from triple excitations. And this generally seemed to represent well-separated electron pairs in molecules like boron hydride or methane, basically quite closed shell structures and nothing particularly dense in electron density. On the other hand, they find these class B systems which have very erratic or oscillatory convergence, and you can see those on the right here. And in this case, they found that most of the systems have very densely packed electrons. So there's a lot of electron density in a small region of space. So this sort of system might be a fluorine atom or hydrogen fluoride or even water. But quite remarkably, it was later found that these class B systems have divergence theories when you include diffuse basis functions. And this is actually quite catastrophic for a theory because we want to add more basis functions to increase the accuracy of our electronic structure. But if we're adding more basis functions in these cases, we're actually getting a method that doesn't even converge. So here is a very important piece of work from Jeppe Olsen, where they look at the neon atom in two different basis sets. And the light circles are a small basis, and the dark circles include the diffuse basis functions. And you can see that divergence starting to appear in the higher orders. So what's going on in these systems? Well, it was later understood that in fact, there is a critical point in your monoplastic series. Now, to understand this critical point, we need to look at our Hamiltonian as a function of lambda. So we have these kind of core Hamiltonian components, which are the kinetic energy and the electron nuclear interaction, and these are independent of lambda. And then we have this repulsive interaction where we have the Hartree-Fock potential, and we're removing it as we increase lambda. And sorry, this is repulsive when lambda is less than 1. And then we have the attractive interaction for negative lambda, which is simply the 2-electron interaction multiplied by the lambda term. And this is being increased as we turn lambda on. And yeah, this is repulsive when lambda is greater than 0 and attractive when lambda is less than 0. So the important thing is to understand the kind of balance of this Hartree-Fock potential with the 2-electron interaction. So the Hartree-Fock potential is generally, well, it's defined by the occupied orbitals. And this means it's usually localized close to the nuclei in our molecule. But the 2-electron interaction is independent of our nuclei because the electrons are always interacting wherever they are in space. And so as we decrease lambda along the real axis, we're making this term, the Hartree-Fock potential, increasingly repulsive and the 2-electron interaction increasingly attractive. And eventually there's going to reach a point where it becomes favorable for the electrons to escape from the nucleus and instead form a cluster of electrons away from the nucleus. And in this case, they have no repulsive energy from the Hartree-Fock potential and a completely favorable kind of bound cluster attraction from this 2-electron interaction. So the important thing to recognize is that this can only occur if we give the electrons somewhere to go. And for this reason, we need to introduce diffuse basis functions, which are able to model that unbound cluster of electrons. But it can also occur if we have kind of a ghost atom in our electrons, in our molecule. And in this case, you might consider hydrogen fluoride, where the hydrogen is a ghost atom to our fluorine atom. So as we have a very negative lambda, the electrons jump from the fluorine onto the hydrogen. And indeed, this can be seen as a quantum phase transition with basically a ground state conical intersection between the two states. So how can we model this in our Hubbard dimer? Well, initially we thought that this was going to be pretty difficult because the Hubbard dimer has no idea of diffuse functions or anything like that. But actually we can do it by using this ghost atom idea. And what we can do is move towards an asymmetric Hubbard dimer where we give one of the sites this positive one electron interaction, attractive one electron interaction. And the strength of that attraction is controlled by this epsilon value, which is always positive. So in this case, we need to use a reference which corresponds to doubly occupying the attractive site, which represents our our atomic configuration. And when we do that, we can find that the continuum is modeled by our empty site, our ghost atom. And if this is going to be a really good representation of dissociated electrons, we want to make sure there's no interaction between the atom and the continuum. So this is a pure ghost atom, and we do this by setting T equals 0. And in fact, T can be used to model how well the ghost site is representing the continuum. So if we take the exact case where T equals 0, we find analytically that the radius of convergence is given by 1 minus epsilon over u. And when this radius of convergence falls below 1, below 1, we're going to get a divergent series. So we can think of this as the electron interaction, how bound they are to the atom, and then also how much the Hartree-Fock potential is repulsive, being controlled by the U parameter. And when we have a very attractive atom and a very repulsive interaction, we're going to get a greater radius of convergence. So what does this look like in some particular examples? Well, here we have epsilon over u is 2.5. And what you see is this sharp avoided crossing occurring on the negative lambda axis. And in general, this critical point is forming as a critical point on the negative real axis, a very sharp avoided crossing. And if we make T 0, this is a true avoided crossing on the negative real axis. And if we make T ever so slightly non-zero, we see that actually it forms this sharp avoided crossing, which corresponds to exceptional points in the complex plane. So here is the T equals 0.1 case plotted as a Riemann surface. And you see there are these avoided crossings in the, there are these exceptional points in the complex lambda plane. So in general, the strength of these two interactions will pull this avoided crossing in towards lambda equals -1, and that will eventually cause the divergence in these diffuse basis functions and for these critical points. And we can look at how the effect of T controls the position of our exceptional point by taking various T values, and we see that the exceptional points converge in onto the real axis. So this is really the manifestation of how a well-modeled continuum gives us an exact exceptional point on the real axis and gives us the critical point in our monoplastic theory. But the incredible thing is that we can also use the same arguments to understand why symmetry breaking in UHF or UMP occurs so close to lambda equals 1. And the important thing to recognize here is that the Hartree-Fock potential is different for each electron because they have different spins. And in particular, the Hartree-Fock potential for one of the electrons, or the spin up electron, is controlled by the electron density of the spin down electron. And so when this Hartree-Fock potential becomes attractive, and this occurs when lambda is greater than 1, we find that there is a positive driving force for the alpha electron to occupy the density controlled by the beta orbitals, and the same for the beta electron to occupy the density controlled by the alpha orbitals. So you essentially get a swapping of the electron density where the alpha and the beta orbitals swap sites, or the electrons swap sites. So for lambda greater than 1, there is this driving force for electron swapping. And there are two ways that this is controlled by the U/T parameters. So firstly, we saw that the unrestricted Hartree-Fock solutions become more localized with larger U/T, and this is a stronger symmetry breaking in the strong correlation limit. So this Hartree-Fock potential is more localized onto one or other of the sites. But the exact electron-electron interaction, which is becoming repulsive along the positive lambda axis, is also becoming even more repulsive for large U. So this is really favoring the electrons never being delocalized over the same site. So for a large U/T, we expect to see this driving force for the electrons to swap becoming increasingly strong until eventually it will happen exactly at lambda equals 1. So as soon as there is any possible driving force for it to happen, the electrons will swap sites with each other. And indeed, if we look at the UMP energies for different values of U/T, so in the solid lines, we're at a very kind of weaker correlation, and we see that this avoided crossing is not particularly sharp. And this is, again, exceptional points not particularly close to the real axis. But as we go to a very strong correlation, we see that the avoided crossings, again, basically become conical intersections on the real axis. So we're bringing the avoided crossing, the exceptional points in towards the real axis, and again we can see them converge in towards the value lambda equals 1. So in the U/T infinity limit, the strong correlation limit, the exceptional point in the ground state interaction will converge on lambda equals 1. And we see at that point that this is exactly why the UMP expansion will always converge, but it will always converge increasingly slowly. So very quickly at the end, we can think about how we might take advantage of this complex structure. And as T2 loves to quote, the most stupid thing you can do with a Monoplastic series is to sum it up. So I'm going to very quickly talk about two ways we can improve the situation. And the first is to use an alternative functional approximation, including a paddy or a quadratic. And the second is to accelerate the series summation using a Shanks transformation. So in the paddy approximant, what we choose to do is say, well, our Taylor series was a pretty rubbish model for our exact MP energy surface. So instead, we might consider building a function as a rational of two polynomials. And here we have two parameters, dA and dB, and these control the order of the expansion on the numerator and the denominator. So this paddy approximant will match our Taylor series expansion up to the sum of these two orders. And we can also model up to dB poles in our function. And this is the great advantage of using a paddy. So what we see if we take our RMP series is that while the Taylor series expansions are not particularly great here in the strong correlation or stronger correlation, the paddy approximants are providing a much better approximation to our exact energy surface. And indeed, we can look at how the kind of Taylor approximations compare to the paddy approximations for different orders of these paddy limits. So here we have what's called the diagonal paddy approximants, where we increase the order on the numerator and denominator at the same time. And you can see our original Taylor series was performing particularly badly for U/T equals 4.5, and this was our divergent series. But if we look at the paddy series, we get actually a much better convergence towards the exact energies. Now, in this case here, we see there's still an error of about 0.003 units of t. So there's actually still quite a large error in the paddy approximant energy. But the second thing we can do is use a quadratic approximant. And the great advantage of these quadratic approximants is that they introduce this square root term. And this square root term we've seen throughout the different areas of the non-Hermitian exceptional points, so it can model those square root branch points. So in this case, we have three parameters. We have the order of our p polynomial, our q polynomial, and our r polynomial. And these match the Taylor series expansion up to a certain order as well. So you can see there are a certain number of branch points controlled by the order of the q and r polynomials. And these occur when the term in this square root goes to 0. And we also see that we can model poles using the q polynomial, and there are up to dq poles on our surface. So in fact, if we look at the R and P energy, the quadratic approximants will perfectly model it. And this is because we had this square root term basically already in our R and P energy. But the UMP energy was much more complicated. But we can look at how well the UMP energy looks by modeling these exact surfaces using the quadratic approximants. So here we're only using the first 8 terms in our UMP series. The exact energy has this 3 exceptional points, 3 branches with 2 exceptional points. And we can take what is called the diagonal quadratic approximants, and we see that it does quite a good job at modeling the blue surface, but it's kind of got this horrible feature of a big pole because we have given Q a non-zero order. So it's trying to model the exceptional points by putting a pole on the energy surface. And you can see that's a kind of overkill. It's doing a lot of work to recover the energy. But we can use the same order of UMP terms and take this, what I call pole-free quadratic approximant. And we see that actually it's giving us a really good representation of these 2 lower energy surfaces. So of course, we only have 1 square root term here, which means we can only model 2 surfaces. It can only do 2 of the energy surfaces at one time. So again, a horrible table of numbers, but don't need too much of it. So here are the UMP terms for different correlation energies. We saw this really slowly convergent Taylor series. So we get down to about -0.3, and we wanted about -0.53. The paddy terms here don't really help us because it's a more complicated surface, and the paddy approximant only has the poles. The quadratic approximant with poles does a remarkably good job at getting down to within 0.1 milli T of our exact energy. And then our pole-free approximants basically get there exactly. So we've taken the first 10 terms in our Taylor series, which were converging incredibly slowly, and we've basically got the exact energy out of the MP expansion.
Hugh, did you also look at how the paddy approximant looks in this complex plane? Would have quite a lot of poles to try to...
Yes, I think it did have quite a lot of poles. Yeah, I think that is an interesting extension. I mean, it wasn't really until I plotted this surface that I appreciated that the poles were actually kind of causing a lot of problems in a way. So yeah, the paddies did have a lot of poles, but yes, I haven't really focused on them in this instance. So yeah, so finally, using these first 10 terms, we're able to see that the UMP energy, Taylor series up to 10 terms has an error of 37%. The paddy terms have 33% error, and you're down to well within 0.01% with the quadratic approximants. Now, the last thing we can do, it's only 2 slides, so we're on the final straight, is take a Shanks transformation of our terms. And essentially all this is we have a series of partial sums, which would be the MP terms up to nth order. And if this series converges, then we know that as n goes to infinity, the partial sum goes to the exact energy. So there's a simple transformation we can make where we take adjacent terms to develop a new series. And this new series should, in certain instances, converge faster to the exact limit. But importantly, the original series must be convergent for this expansion to work. So in fact, this doesn't really help you with the UMP series, either because the Taylor series is too slow, or the paddy series is too bad, or the quadratic series is too good, that you don't really get any acceleration at all. But it does help us with these first 10 terms of our RMP expansion. So in this case, we had a divergent series originally. But when we took the paddy terms, we have a new series that is now convergent, but slowly convergent. So we use up to 10 terms to generate we use 10 Taylor series terms to generate 5 terms in the paddy approximants. We take these 5 paddy terms to generate 3 terms in a Shanks transformation. And you can see that what we had as 0.76277 becomes 0.76042. So we've now reduced our energy of the divergent RMP series to an error of 0.002%. So by taking the original terrible RMP expressions, understanding the structure in the complex plane and using that to build a better approximant to our energy, and then accelerating the convergent series, we've managed to get well within kind of what would be regarded as acceptable accuracy out of what was originally a pretty dire situation. So with that, I'd like to wrap up and obviously thank Titu and Antoine for their help with this piece of work. Obviously, my employers in Oxford require thanking, and yeah, we had this paper out, and a shameless plug to follow me on Twitter. Thank you very much.